All right, physics party people. This is a problem that was on the energy and momentum combined assignment that I just got a lot of questions about or overheard a lot of people that were having trouble with it. So I just wanted to quickly walk through this. Shouldn't be a long video. This problem combines the conservation of momentum and the conservation of energy. Okay, a rocket needs to reach 25,000 miles per hour or 11,000 meters per second to enter Earth's orbit. If a 2.2 times 10 to the 6 kilogram rocket were to instantly eject a single 20,000 kilogram object to enter orbit starting from rest, how far does the ejected object go if it's slowed down with a frictional force of 400,000 newtons? Okay, looking at how far does an object go? How far does an object go? How far, that is our displacement. And we know, we're told the frictional force. So if we know force, we want displacement. Those two things right there together tell me I'm probably looking for my work or my change in energy. So I'll probably use energy initial, and if it's frictional force, we're taking energy away. So minus work is energy final. Okay, so there's kind of our setup there. The problem becomes, right, we want it to come to a rest. We want the frictional force and the displacement. The problem becomes we don't know how much kinetic energy this has initially. So we have this 1/2 mv squared, mv naught squared. We know the mass of this ejected object, but we do not know the initial velocity. That's where we're going to have to use what we know about the object and the rocket interacting. So essentially, the problem is set up. Um, we're going to see if I can draw a rocket here. Okay. Um, Here's our rocket. Pretend like I'm a good artist because we all know that that is a lie. Okay, so there's our rocket. Um, all right, we're going to say that this rocket instantly ejects just a single box. So the rocket will fly off this way, and the box will fly off this way, starting from rest. So that tells us this is what we would consider in physics to be this term explosion, where explosion just means two things start at rest together and then something separates them. One goes one way, one goes the other. We know that in an explosion, our momentum must be conserved. So our initial momentum is zero. Final momentum, we have the momentum of the rocket and we have the momentum of the block, or I should say of the object. We aren't told that it's a block, but the momentum of the object. Okay, so right, our momentum of our rocket will be to the left, momentum of the object will be to the right. Essentially, what we can say, since one of those will have to be negative, depending which way you call positive, um, we can say that whatever our momentum to the left is after must be equal to the momentum of the right. So momentum of the rocket has to equal the momentum of the object after that explosion. Okay, so m rocket v rocket must equal mass object velocity object. Okay, so our mass of our rocket is 2.2 times 10 to the 6th kilograms. It must be traveling at 11,000 meters per second to make it into orbit. We are then told that a 20,000 kilogram object is ejected, and we want to know how quickly is that object moving? What's the velocity of that object there? All right, I'm going to plug this into my calculator. 2.2 times 10 to the 6th times 11,000 divided by 20,000. I get 120, 1210 with three more zeros. So a million meters per second. That is fast. That is a fast moving object there. But now we can plug this in over here. So I'm going to bring this up and say that our velocity of our object, we now know what it starts at. So let's take a look at this problem then. So we have our initial kinetic energy, 1/2 mv of the object squared, minus the work, which we can calculate through force times displacement, gives us our final energy, which is nothing. It's coming to rest. Okay, 1/2 mass of this object is 20,000 times initial velocity, 1,210,000 squared. Okay, minus force of friction, which is 400,000. And we're looking for displacement, and that all has to equal 0. So 1/2 times 20,000 times that over 1,000,000 meters per second squared. So here I get 1.46 times 10 to the 16th is that term. I will add 400,000 d to both sides plus 400,000 d to both sides. Okay. So that cancels out with that one and sends it over to the right side. Now we can find our displacement by dividing by that 400,000. Okay, so I get 3.67 times 10 to the 10th. 3.67 times 10 to the 10th, it's a displacement, so meters. That is a lot of meters. All right, but there's our displacement. To put this in perspective, the circumference of the Earth, and I'm looking this up right now just to make sure that I have this correct. The circumference of the Earth in meters is just over 40 million, so 4 times 10 to the 7th. So if we're looking at this, this is almost 4 times 10 to the 10th. So we're going around Earth about 1,000 times if this is the case. So this can't possibly be realistic, but it's a good physics problem, right? We combined our explosions and our conservation of momentum, and we combined our conservation of energy using negative work on a single object. Right? The conservation of momentum was for a system, and that's a closed system. There's no outside forces. Then we're just considering the system of the object to go ahead and do this energy expression over here, system of just the object, with the external force of friction, and that is what gives us our final answer there. All right. That should do it for this problem. If you have any questions, please let me know. Otherwise, see you next time.